Okay. Okay. So as I was saying, I'll go through this example. This example where G of S is actually open loop transfer function, and then we have K over S into S plus 1 into S plus 8. So what you need to do, first is to identify the poles and zeros. So from that expression, oh boy, from that expression, we can identify poles. So this is what normally I do. I write poles like this, and then identify the poles. So from here, I can clearly see that we have, for me to get the poles, this is maybe some guys, they don't know. So you just equate the denominator to 0. So you say S plus 1, S plus 8 is equals to 0. And then from here, it is clearly that 1S is equals to 0, another one is minus 1, and another one is minus 8. So these are the poles. So you equate the denominator to 0 and then get the roots of it. So from here, I can say I have one pole at 0, one pole at minus 1, another pole at minus 8. Then from here, what I say, I indicate the number of poles. So I have 1 pole, 2 pole, 3rd pole. So Agnes, I can see you are raising your hand. So from the denominator, you equate the denominator to 0 and then get the roots. So from there we have S is equals to 0, S is equals to minus 1, and third one, S is equals to minus 8. So those are the poles. And immediately after that, you can indicate the number of poles. So you say the number of poles is equals to 3. And then you go to zeros. And then when you look at this, guys, is there a problem? I can see some people are raising hands. Hello?
No,
okay.
Hello, there's no problem.
Okay, so next you go and check if there are any zeros. So the way you get zeros, you equate the numerator equals to 0 and then get the roots. But from this example, it is clear that we have no zeros. So you say nil. Number of zeros, nil. And then we don't have any zeros, and then number of zeros is equals to 0. After that, you indicate these poles and zeros on your axis, on this axis. So first one is this one. So I say, and normally you indicate a pole with an X. So at X is equals to minus 1, you say this is minus 1, and then obviously another one is minus 8. After that, you look at that, you check if there is any locus along the real axis. So here you apply which rule? You check rule 4. Rule 4 says a point on real axis is part of a locus if the number of poles and zeros to the right of the point is odd. So the way I explained last time, you stand here and look in right direction, in that direction, this direction, and then you count number of poles and zeros. So how many poles and zeros are there in that direction? Someone to answer that.
1.
1, which is odd, right? So it's odd. If it is 1, it's odd because we just have this one here. So that is odd number. So if that is odd number, then it means this segment here, this line here, is actually part of root locus. And let's say you stand here now and look in that direction. How many poles and zeros are in that direction? We have 2, right? And 2 is even. So it means this part is not part of root locus. And then you go and look at that direction. You stand there and look in that direction and you count numbers of poles and zeros. So number of poles and zeros are actually 3, which it means is odd. So this part is part of root locus. And remember, we said in rule 2 that a pole root locus starts from a pole goes to a 0. So if this pole will go and look for a 0, and this pole will go and look at for a 0, and also this one will go and look at for a 0 to terminate. So this will go to infinity to look for a 0. But these 2, one will come this side to look for a 0, another one that to look for a 0, and then they will break. They will break. We don't know in which direction they will break. And we don't know at what point it will, they'll break in or break out. Sawa. So next, what I normally do is I get number of directions, lines of direction where my root locus will, where my root locus will pass through. So we call those asymptotes. So the number of root locus, the number of asymptotes. So what I do, so I say number of is actually number of poles minus number of zeros. So how many poles do we have? We have 3. How many zeros? We have 0. We have nil zeros. So the number of asymptotes is 3. And then for me to calculate the direction where these asymptotes break through from the real axis, I need to calculate using this formula. 2n plus 1 pi over number of poles minus number of zeros. But I know this is, we have how many asymptotes? 3, right? So for me to use this formula, my n always starts from 0. So I'll have first angle, n is equals to 0. Second angle, n is equals to 1. And third one, n is equals to 2. where 0, 1, 0, 1, 2 represent these three angles, or or number of asymptotes. So let's say your number of asymptotes is 2, then you'll calculate for n is equals to 0 and n is equals to 1. Is that clear? So here I'll say for phi 0 is equals to, I have my n0 here, so I have pi over what? Pi over 3, that is 180 divided by 3 is 60. And then another one, phi 1, this will be 180, and then phi 2, this will be 300. And 300 is the same as minus 60, as I explained yesterday. So this number of asymptotes, the direction where which locus will follow, will have these angles along the real axis. But we don't know where these angles intersect or start on the real axis. That's where the centroid come in. Centroid. So centroid, we need to find a place somewhere on the real axis where we can draw these 60 degrees, 180 and 300. So we use the centroid. So centroid is sum of poles minus sum of zeros divided by number of poles minus number of zeros. So sum of poles is what? So we have our poles here, 0 minus 1 minus 8. So we sum this. 0 plus minus 1 is minus 1. Minus 1 plus minus 8 is minus 9. And we don't have any zero, so it's just minus 0. So we have minus 9 as our numerator. And the number of poles minus number of 0 is what? Is 3. So these angles actually start somewhere. So this, let's say this is minus 2. So we have this minus 3. So we'll have our 60 degrees here. Another one is minus 60. And then we have a 180 as this one. So, and this one is where this one follows from minus 8 to infinity. So our root locus will pass along these lines. Is that clear? Someone was asking yesterday about these lines. Before I proceed, is that clear?
Excuse me, sir.
Yes.
Could you kindly repeat where negative 9 has come from? Sum of poles minus sum of zeros.
So, as I was saying, after getting the angles where our asymptotes will intersect the real axis, we need to get at the point where those lines will intersect. So normally what we do, we use this formula, centroid. So centroid is given by sum of poles minus sum of zeros. So this, you add all the poles. So these are our poles. We have one pole is equals to 0, another one minus 1, and another one minus 8. So we add this 0 plus minus 1 plus minus 8, we have minus 9. Sawa sawa.
Yes.
And the denominator is the number, not the sum, the number. We have how many poles? We have 3 poles. So denominator is the number of poles and zeros. That's why I put this hash, right? So how many poles we have? We have 1, 2, 3. How many zeros? We don't have any zeros. So like that. So that's how we get the minus 3. So this, and then you draw your angles, like one is 60. And class, just excuse me, one. Hello? So, sorry about that. So, is that clear how we get the centroid, right? Now,
Yes.
We know that where our root locus direction goes, like we have, obviously for this 180, you can see we have this one goes as 180. And other one will follow this line. But we don't know where these two lines, where these two poles break and follow these two directions. So we need to get this intercept. And that is the rule number 7. Rule number 7 says the breakaway point or the breaking point between two poles, between these two poles, this one and that one, along the real axis is the point at which the variable, this is the variable k, the variable of intersect, which is k, is at a maximum. Okay, it's a long description, but it's very easy. So the way we do this is actually get the k over the s. So we get the k over the s, and we can get the k over the s from the characteristic equation. So this is the characteristic equation. What you have here is this, you see, this part, which is this one, right? So this is how you do it. So you say 1 plus the whole of that is equals to 0, right? And then you say s plus 1, s plus 8 is equals to 0. So you have s squared into what? Sorry, you have s into s squared plus 9s plus 8 plus k is equals to 0. That's how I need to rub some of this. So let me rub here. Okay. So you make k the subject. So you'll have k is equals to minus s squared plus 9s plus 8 is like that. So you have k, cubed plus 8s. And then from here, you can get your derivative, dk over ds. So the k over the s, you have minus outside. So you have 3s squared plus 18s plus 8. So you set the k over the s is equals to 0, which means I don't know if that's correct. So if you solve this, someone can help me. If you solve this, obviously you'll have two roots, one outwards and one out. So someone to help me with the roots.
I got negative 0.483.
Negative 0.483.
And negative 5.5166.
Negative 5.5166, also negative 5. Okay, so from these two points, these are actually the points where you see here. So let me just so I have, is that a real name? Peace Joy. So you have S is minus 0.483, and we have another S minus 0.55. So we have two points, and here we just have one break. Okay, there are only two poles meeting together, so it means there is one breakaway point. So among these two, yes.
S2 is negative 5.5, not negative 0.55.
Oh yeah, negative 5.5, right?
Yeah.
Oh, negative 5.5, like that.
Yes.
So from these 2 points, which one is along the root locus? Because we know on our real axis between 0 and -1, this is part of root locus. And then we don't have anything between -1 and -8, and -8 to infinity is part of root locus. So it means this point here is not valid because it is around here between -1 and -8. So it's not valid. It's not part of root locus. The only valid point is this one. That is so this is valid, and this one not valid. Why? Because it's not part of root locus. -5.5 is around here, which is not part of root locus. So this minus 0.48, it's around here. So it means these two lines, these two poles come and break to follow they come and break. No, not like that. They come.
Excuse me, sir.
Yes.
Is it possible to get two breakaway points for two poles?
Is it possible to get?
Two breakaway points for. Hello.
Yes.
Is it possible to get two breakaway points for certain poles?
No, these are breakaway points. Like you see, one pole, this pole. We know that a pole will always go and look for a 0. So this one will come to look for a 0, and also this one will come to look for a 0. So they'll meet somewhere. That is the breakaway point. So for a pair of poles, we'll have one breakaway point, because this is the point where they meet. So always it will be 1 here. Okay, for this case is 1. Is that clear? So when they reach here at minus 0.48, it will break to follow what? To follow these asymptotes. So we'll have something like this. So this is a pole, and that is a pole. This is minus 1, that is minus 0. So this one will come and break like this, and this one will come to look for a 0. Along what? Along these directions, along these lines. Sawa sawa? Hello?
Yes, sawa sawa.
Okay, so we have that. We don't know where they intersect the J omega axis. So we need to find this. We need to find this point. This point. And you already know that. You know how to find this point, right? From what? From the how it's criteria. So what's this point? Yeah, I can do it here. So from this characteristic equation, you open it up. So you have s power 3 plus 9s squared, yes, plus 8 like that, plus k is equals to 0, right? Yeah. And then you draw your table. So you have 1, 8, 1, 8, and then you have 9, k. So this one will be k, and this one will be 72 minus k over 9. You can check if that is correct. Someone to check if that is correct.
Pardon, what are we?
Sorry? Hello?
It's correct.
Okay, so you remember we said for us to get intercept at j omega axis, or to have a marginally stable system, is when one full row of the root how it's stable equals to 0. So for us to have a row here in this table equals to 0, then k here needs to be 72. So if k is 72, it means this will be 0. So the whole row will be 0, because here we don't have anything. Here it's also a 0. So if we have a full a 0 row in a root how it's stable, then it means we have a marginally stable system. And a marginally stable system means we have a point on j omega axis, right? So for us to have this 0, k needs to be 72. So if k is 72, then we take the upper row, which is an auxiliary equation, and we'll have our
Excuse me, sir. Why can't we set the s power 0 to become 0, to be the 0 row?
We can't, because we have 9. We need a whole row to be 0.
Oh, and the s power 0, it has just k. So if we set that one to 0,
K is a constant. Remember
Oh,
our
the constant.
K,
Yeah.
remember our K is greater than 0.
Oh, okay.
Who's that? Nani huyu anacheza na watoto? Kim. You get it now. So because this is greater than 0, if it's 0, then we don't have any system. The whole of this goes to 0. So we take this equals to 72. If that is 72, then we'll have our auxiliary 9s squared plus 72. So we say s is equals to 0. 9s squared plus 72 is equals to 0. We'll have s squared is equals to minus 72 over 9. So minus 72 over 9 is what? So I think you'll get your s equals to plus or minus j 2.833. So you'll have your s at plus or minus 2.83. So your point here is j 2.83, and here is minus j 2.83. So that is how we plot root locus, or we sketch. And remember, you can actually draw this on a scale using a graph. So all these, if they're up to scale, so you can draw using a graph or just sketch. So when I say sketch, you can just sketch and just give all steps. If you have to draw so that you get some dimension, this and this, then you have to use graph paper. Any question on that?
Excuse me, sir.
Yes, yes.
I have a small, like, just to take you back a bit, where you're getting the equation here, the last part, A.
Okay.
The
Here.
auxiliary part.
Here.
Repeat. No. Yeah, this, could you please repeat there? I've not quite gotten it.
So I start from the route table.
Yes, just the part where you've gotten the equation for 9s squared plus 72.
Okay. So since we say that a k is, for this to be 0, this row to be 0, k needs to be 72, which is obvious here. 72 minus 72 is 0, so this row will be 72. So our k is 72. So if our k is 72, we'll have that is equal to 72, and that equals to 72, right? This row, if k is 72, this row will be 0. The whole of this row will be 0. So the row before it is actually where we get our auxiliary equation. And remember, we say auxiliary equation always will be even, as in s power 2, s power 4, like that. So the first coefficient here is s power 2. Here, s power 2. Next one will be s power 0, because it needs to be an even, as we say, auxiliary equation will be even. So that's why I say auxiliary equation here, the first one is 9, this one 9. This is how we do it, 9, and then you take that. So 9 plus what? Plus 72. So next one will be just s to the power 0. So for you to get these roots, obviously for you to get roots, you set a of s is equals to 0. So we say 9s squared plus 72 is equals to 0. So 9s squared is equals to minus 72. S squared is equals to minus 72 over 9. So the j comes because of this minus. We know the minus squared is j, so j s is equals to plus or minus j because of this minus here, 72 over 9. And then you get your 2.83 j plus or minus because of square root. Madam, is that okay? Hello? Hello?
Yes, that's okay.
Okay. Anyone else? Before we start, another problem where there is some angle of departure and angle of arrival. Before that, I need to show two other methods for you. There is a method where you can get this point. Where is it? You can get this point here, the breakaway point, without going into trouble of dk over ds. And also there is a way you can get this without using this table. Without using this table. Is that clear? I just want to show those two methods. I know they become handy when you have a pole. Let's say you have a pole here, and then if you have a 0 and you make k the subject, then you'll have an equation where you have numerator and you have a variable in numerator and denominator. And differentiating that is it's not a challenge, but it's involving, as in you need to you remember those pure mathematics. U over v differentiate uv minus vu over what? So to bypass that, there is a method where you can get this breakaway point without going into differentiating and stuff. And also there is a way you can get this without formulating this table. So if you're okay, I can show you that method. Everyone is okay? I proceed. Hello? Andrew? Okay. So let me just go to a new section. So remember, so this is just, you can say, method 2 for breakaway or break-in point. So this you work from the open loop transfer function. So open loop transfer function, we know our open loop transfer function is So from here, we know our poles is S is equals to 0, S is equals to -1, and S is equals to -8. These are poles. Poles, we don't have any zeros. Zeros is nil. So we use this formula. Don't be alarmed. It's very simple. It's simple. So you use this. What it says, these are the number of poles, and n is the number of zeros. So what it says is, we know how many poles we have: 1, 2, 3. So the first one, what you do, you say S is equals to 0. So the pole here is 0. So you just have X. Another one is S is equals to -1. So you have X plus minus -1. So you have X plus 1 plus. And then another one is S is equals to -8. So you have X minus -8, like that, is equals to what? We don't have any zero, so is equals to 0. Like that. So you solve that. So the way you, it's simple, you say L. Like that. You multiply each term by the product of this. Here you have X plus 8. And here you have X plus 1 is equals to 0. So we'll have X squared plus 9X plus 8 plus X squared 8X plus X squared plus X is equals to 0. So X, we have 3X squared. 9X plus 8X is what? 17 plus this one is 18. 18X plus what? Plus X. Plus what? Plus 8, right? Guys?
Yes.
So you can see this is same as the equation you got. So if you find your X, you'll get minus 0.483, and another X is minus 5.5. So you can get K and do dk over ds, differentiate, or you can do this way. So if you have a pole here, if you have a zero here, then you'll equate same way like this one on the other side with a 0. Like if you have a 0 of -1, then here you'll have on the right hand side of the equation, you have 1 over X plus 1. Is that clear?
Yes.
Okay, so you can do this if you have an open loop equation where you have zeros and poles, because differentiating when you have a numerator and denominator, I know it's a challenge. Any method you find comfortable, you can use. Another method you can method 2 for J omega axis. So what you do is you get characteristic equation. and then you substitute S equals to J omega. So for our side, we'll have S plus 1, S plus 8, plus K is equals to 0. So we'll have S squared plus 9S plus 8 plus K is equals to 0. So we have S cubed 9S squared plus K is equals to 0. So you substitute J omega cubed squared like that is equals to 0. So here we'll have minus J omega 3 minus 9 omega that J omega plus K is equals to 0. So you group these together. So you'll have J 8 omega minus omega cubed from this guy and that guy, and then plus K minus 9 omega squared is equals to 0. So you compare right hand side and left hand side. So since is equals to 0, then it means 8 omega is 8 omega minus omega cubed is equals to 0, and also K minus 9 omega squared is equals to 0. So from here, from this guy, sorry, from that guy, we can say 8 omega equals to omega cubed. So 8 is equals to omega squared. So omega, like that. I think that is 2.83. Someone to check. Please, someone to check.
Yes, 2.83.
So that is 2.8. So you'll just know 2.83. You know your omega here from the, this is 2.83, and that one is minus 2.83. And then also from this guy, we'll have K minus 9 omega squared is equals to 0. So you'll have K is equals to 9 omega squared. But what is our omega squared? Omega squared is 8. So we can also get our K as 72. So at this point, our K is 72, same as the other method. Sawa sawa. Hello?
So,
Okay. So you can use either method as whichever is comfortable with you, but I urge you guys you practice. You need to practice. So from the notes you can select which one we should go through, and then we end this lecture. We go through one problem. Hello?
Page 15 of the notes.
Page 15.
Yes, the equation given.
But okay. Yes. The one we say, consider a unity feedback control system with the following feed forward, right? Yes, madam.
It's the PPT one. It has a K over S into S squared plus 2S plus 2.
Plus 4S plus 8.
Plus 2S plus 2.
K over S into S squared plus 2S plus 2.
Yes.
Okay. So let's do that. So you are told draw root locus for a system having the following open loop transfer function. Obviously here we assume that it's a unity. Okay, it's a unity feedback. So a unity feedback means h of s is equals to 1. And the open loop is given as g of s is equals to k s squared plus 2s plus 2. So first, remember I said you locate poles and zeros. So zeros, you say nil. Number of zeros is equal to 0. Pole, so you need to factor this one. You need to factor that. So you say s squared plus 2s into factor form. Obviously, you can use your calc. Just get roots of these from your calculator, and then you get these two factors. So the denominator now we can write it as this. So poles we have pole at s is equals to 0, at s is equals to -1 plus j, and at s is equals to -1 minus j. So we have how many poles? We have 3 poles. So we have 3 poles, and we have nil zeros. Next, number of asymptotes, which is the number of poles minus number of zeros, which is given by 3 minus 0, which is 3. So if it is 3, then it means our n will start from 0, 1, 0, 1, 2, 1, 2, 3, 3. So the directions is given by that. So at phi is equals to 0, at phi 0, which n is equals to 0, we'll have 60. 1, we have, 180. And phi 2, we have 300. So next, so you'll draw these, you locate this point. So 1, 1, 0 at that point. So this is j omega. Another one is, let's say this is -1, and that one is also -1. So we'll have -1j at that point. So this is j, and that is -j. So next you look at the real axis and locate root locus. So if you stand here, there is no poles and zeros in that direction. So this is not part of root locus. If you stand here, there is only one pole in that direction. So it means the whole of this line here, the whole of that line is part of root locus. So this guy will go and look for a 0. Remaining are these two. So from the diagram, it's clear that we want have a breakaway point because there are not two poles on the real axis which they face each other. So there is no breakaway point. Even if you calculate, you try to calculate breakaway point, you'll find that they are not along the real axis or any part of its locus. We can, okay, the angles, we can get centroid, which is sum of poles minus sum of zeros, number of poles minus number of the zeros. So sum of poles, you add, you say you add this 0 plus this, 0 plus that, plus that. So let me just do it here so that you can see. So you have 0 plus minus 1 plus j plus minus 1 minus j. So when you add this, you can see that this guy and that guy will go. So we have minus 2. We don't have any zeros, so it's just minus 2 minus 0. So we have minus 2. And here it's 3 from there. So this is, I think, minus 0.66 recurring. So you can say minus 0.7. So that is minus 0.7. So we'll have, let's say here it's minus 0.7. So these are just dotted lines. These are just to guide you. 300 is the same as minus 60. So we know that this pole will follow that line, and also that pole will follow that line, but we don't know the angle in which this pole will actually leave, the departure angle. So we need to get this angle, the departure angle. If your diagram is to scale, there is a geometrical way of getting the departure angle, but I'll prefer doing analytically. So let me just rub some. So according to the equation I gave you, I didn't give you last through the notes, but coming notes, which I'll post maybe Monday. So the angle of departure, this is how we calculate the angle of departure, is equals to argument open loop transfer function like that plus 180. So you get argument or angle of open loop transfer function excluding contribution of that of the point where you are calculating. Let's say we want this angle of departure here, and we know this point S is minus 1 plus J. So you get argument of G of S, G of H, but excluding contribution of that point where you are calculating. So in short, the way we do it is we know our K, so we say argument K S, we have S plus 1 minus J, S plus 1 plus J. So this point is actually S plus 1 minus J, right? So you calculate at this point, but excluding contribution of this. So what you say is you multiply by S plus 1 minus J to exclude contribution, and then you get that angle, the argument at that point, plus 180. So if you are finding at this point, then you need to remove that that contribution, and that you just multiply by that point so that it cancel each other, and then you calculate the argument at that point. So you say theta, or angle of departure, it is K. So this guy and that guy will cancel, and S at this point, so you have minus 1 plus J. And here, when you add S here, the real will go, so you have 2J plus 180. So you get argument of this plus 180. Someone to do that. So what? Someone to help me with that using calculator. Hello? You guys are there?
It's √2/4.
Argument, angle.
The angle is 135 degrees.
135, huh?
Yeah.
So everyone knows how to get that.
No.
So what normally I do is I set my calculator as a complex mode, mode complex, and then I type in the denominator, this denominator here, which is minus 1 plus I into 2I. So I get that value, and then get the inverse. Just you tap the x to the power minus 1. And then what normally I do? I say shift complex and select 1. I get 135. So that one you can Google how to get argument there. So 135 plus 180. So 135 plus 180 is what? Is 315. 315. So since we are measuring angle in anti-clockwise direction, so we will measure 90, 180, 315, maybe at that point. So this line, this point will depart from the 135 degrees like that, which is same as minus 45. So if you have here as minus 45, minus 45 is equivalent to 350. So the angle here also is what? Is for, if this is minus, then the angle here is 45. Sawa sawa. Hello?
Yes. Yeah, it's okay.
Yeah. So another thing is to get this J omega axis point intersection. So you can use.
Excuse me, sir.
Yes.
I have a question.
Yes.
How did you in the equation for angle of departure?
Yes.
Where did S plus 1 minus J in the numerator come from?
S plus 1 minus J.
Yes.
Okay, from here, this is our open loop equation, right? So we factor this.
Yes.
We factor the quadratic equation, we got this. So.
Yes.
And then we said for us to get angle of departure, we calculate argument of open loop transfer function plus 180 at that point where we want angle of departure, but without contribution of it. So this one, so we are calculating at this point, which is same as, right? This point. It's same as this. Sindio?
Yes.
So we don't want that the angle contribution of it. That's why we multiply by S plus 1 minus J to remove this so that they cancel. You understand? So the remaining, yeah. But we are calculating argument at that point where we are excluding its contribution. So which is this? So we substitute the S's here, and here to get, and then the argument plus 180. Sawa.
Yeah, yes.
Excuse me.
Yes.
When you're sketching the curve, when you're sketching the two curves,
yes.
Where does the change in direction really occur? Is it at the centroid point, or where do you sketch the change in direction of the curves?
Which these curves?
Yeah.
That's why we are calculating the angle of departure. So at 45, it will move this like that along these lines, along the asymptotes directions. So at the same time, let's say you know your intercept, which you need to find. So if let's say I know my intercept, it's around 1.4, and obviously maybe this point is here, and the direction are along this point, around that point. So we have 45. So I'll say it will go like that, as I'm forcing it to intersect the 1.41, the J omega axis. So the J omega axis will help me to know where it will pass through. Also, this direction, I'll know that it will go in that direction, and also the angle of departure, which is in our case is 45. So we know that it will go along that 45, not along maybe 180 here. I know it's along 45 like that. and passing through the j omega axis at that point. So you need this point, you need these lines, and you need that j omega, you need that angle of departure. And then guys, you can, if you know MATLAB, you can try to plot these on MATLAB so that you confirm what you have and you play with it. I think the command in MATLAB is rlocus, but you can, and then you have your transfer function. You can go look at how to plot this in MATLAB. You'll do this, I think, with Mr. Kinyua in Control Labs. But it's easy. You just go Google how to plot locus in MATLAB. Any other question?
Just a quick question.
Yes.
I'm trying to understand what really does the angle of departure and arrival mean physically, like hypothetically speaking. What do they represent?
No, the angle of arrival and angle of departure. Remember, all these rules help us to draw root locus. Okay, it's an old rules where you know, before we didn't have, long time ago we didn't have computers where you can just plug in R locus with your transfer function and get root locus, right? But these rules help those guys, the control system designers, to plot root locus. I won't go into how the departure is, okay, according to syllabus, we are not supposed, or it's not part of syllabus that we know, we look at the derivation or the derivation of angle of departure formula, but what you can appreciate from this point is that these are rules or tools to help us sketch root locus. And the beauty of root locus is that once you have your root locus as in proper dimension, as a scale root locus, then we can use a frequency response specification, and we can also use time domain specification for us to get parameters. Like if you are told, okay, you have plotted this system, and then you are told to find, you want to find K, maybe for a damping ratio of 0.6, right? We know that cos of theta is equals to 0.6. 0.6 is the damping ratio. So if you get theta from here, you can actually draw a line with that angle theta, and then get this point. This point is actually the K, which will give you this damping ratio from the time domain specification. I don't know if I answered you, but the angle of departure and arrival actually help us to draw root locus. Madam.
Yeah, I think that's okay.
The most important thing is to know how to sketch, as in this control system A. Actually, what we do is just analysis and having those tools. So make sure you know how to draw this, both in MATLAB and the way we are doing right now, because this is what I'll test you guys.
Excuse me.
Yes.
When you're testing the root locus questions, do you only use open loop transfer function?
Yeah, we always use open loop transfer function in formulating root locus. By the way, why, you know, why we are using this is, let's say we have our G of S is N1 over D1, and H of S is what? Is N2 over D2. Therefore, our characteristic equation is what? Is GH, right? Right? So we'll have N1 D1, no, N1 over D, sorry. We'll have N1 D1 multiplied by N2 D2. So we'll have D1 D2 plus N1 N2 is equals to 0 divided by D1 D2. And if we are finding a closed loop, so for closed loop, we'll have D1 N1 like that. And here we have what? We'll have N1, G1 plus GH. So here we'll have N1 D1 over D1. And this one will have what? We'll have N1 D2, N1 N2 D1, like that, right? So if you multiply by this, we'll have N1 D2 D1 D2 plus N1 N2. So this is closed loop control system. And open loop is what? Is N1, yeah, N1, what? N1 D2 and what? D1 D2. So from the characteristic equation, you see this characteristic equation. So from the characteristic equation, you can see that the numerator roots, these roots of numerator, which are zeros, are actually what? Are actually the closed loop, what? The closed loop poles of the closed loop poles of a transfer function. So we don't need to go through this one to get this. We can actually get the roots which are the same from the open loop transfer function. That's why every time when you are plotting root locus, you are told open loop transfer function is this, because from the open loop transfer function you can actually get the roots of a closed loop transfer function, which is just the same. We see that in frequency response. But all questions which I'll give will be like a unity feedback, or I'll give you G of H is this with a K, and always K will be greater than 0. So in our case, we'll consider K is greater than 0 for root locus. So I'll either say unity feedback with open loop G of S, or I'll say open loop transfer function as G of H is equals to blah, 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 like that. So if you practice this, you'll have something like 10 marks. And maybe from Roots Locus, you have another 10 marks. I normally don't give questions exam for reduction of block diagram. No, those are too simple. Maybe time domain you get, if you have those circuit RLC, you get there again 10 marks. So you have like 30 and cut. So if you practice well, it's an easy pass unit. But people fail. People fail. So.
Sir?
Yes.
Will you kindly repeat on how you related the value K with the damping ratio in the root locus diagram?
Oh, the value K with damping ratio. So if you have J omega like that, so damping ratio always equals to cos theta, where theta is this. So if you have a damping ratio of 0.6, your theta is cos inverse what? 0.6. I think is what, 53?
53.1.
Yeah, so you have 53. So let's say your root locus passes like this. And remember, root locus is actually the roots as we are varying K. So the whole of this point is K, 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 K. At this point, remember in previous example, we got this K as 72. So you can be told for a damping ratio of 0.6, find the value of K. So you need to find this value here. So the way we do this, let's say here we have a pole, and maybe here we have another pole and a pole, and maybe a 0. This is just example. So you can find K. So you measure from each pole. Let's say this is A, B, C, and that is E, and this is D. So you measure angle, you measure length from A to E, multiply from B to E, multiply from C to E, divide by from D to E. So all these are the poles. So the poles are on the numerator. From this pole to this point, you find the distance. From here to here, you find distance. From there to there, you find distance. So these are all length contribution from the poles. And then you divide from length contribution of zeros. And then you get your K. But it has to be on scale. So when you are drawing this on scale, make sure for each unit, let's say you can say 1, 2, 3, like that. 1, 2, 3. So if you have like, you want this to be 1, and this 0.5, same thing, you do it here. And then you divide this, each contribution by 2 because of this unit, because 1 unit is actually 2 centimeters. So you divide, so the centimeter you get, you divide by 2. So the way I normally do it, I just do it with 1, 2, then 1, minus 1, minus 2, like that. from the graph. So from the graph, it's easy if you have uniform scaling here, x-axis and y-axis. So when you draw your 53 degrees, and let's say your line passes that one, so you just from this pole to here, get your length from the ruler, that one, that one, that one, you multiply, divide by contribution by 0. That's how you do it. Is that okay? Is it Kembo?
It's okay. So that means, for example, the exam question you sent, it means that we have to find a graph paper for that.
Actually, I'll give you graph paper for that.
Oh,
it's exam.
Okay.
It's the exam.
Okay.
I'll give you graph paper for that.
And then last clarification. Yeah, so you said that this root locus just shows how we vary k. So that means it for example, if our k ranges from 0 to 72, it means that where it intercepts the j omega axis, that is for 72.
Yeah, 72. You
and,
remember?
And then
you remember we
got I remember
like this.
Yeah.
Yeah.
Yeah. Yeah, makes sense. And then another clarification I wanted was, so it's at that same point that you also have the frequency that we calculated.
Yes. So at this
okay.
at this point, at k is equals to 72, you'll have omega is equals to what? 1.4? How many? 2.8?
Well, 1.44.
1.4, right?
No, 4.
Okay,
no,
any.
it was
2.83.
8.
Yeah, 2.8, 2.83. So at this point, omega is 2.83. And also, if you have k is equal to 72, you'll have 2.83 as frequency. And since it's on this omega axis j omega axis inter, it means the system is what? Marginally
stable.
It has sustained oscillation, as in there are oscillation throughout with this frequency. Sawa.
Makes sense. That makes sense, sir. Thanks.
Okay. If you're okay, I can just give you one problem. We go through it without doing all. I just need you guys to see something and then we wind up. Can I proceed?
Yes.
Okay, so there is one problem. Maybe you can write as it say the block diagram. You can write the block diagram. The block diagram of a position control system is shown in figure below. Draw the root locus for the system as parameter alpha varies from 0 to infinity. So this is just to say alpha is greater than 0 or k is greater than 0. And hence, determine the value of alpha so that the damping ratio is 0.6. So the diagram is like this. So we have 10 plus alpha over S into S plus 6 So this is plus minus R of S. So you are told to draw the root locus for this system as you vary alpha. So one way to do this is getting is expressing this. You try to get something like this, which in your case will be and you know your H is what? Is 1. It's unity feedback. This is just 1. So your G of S is multiplied by, so you'll have 10 alpha. No. You'll have 10S alpha over S plus 6, like that. So 10S alpha S squared S plus 6 as GH. So this is our GH. So you proceed and say is equals to 0. So we have 10S alpha equals to 0. So you simplify this. Is equals to 0. So you'll end up with S cubed S squared plus 10S plus alpha is equals to 0. So you divide by, these are just tricks. So you'll end up with 1 plus alpha S cubed plus 6x squared plus 10s is equals to 0. So this now is similar to what we normally have. So from here now, you can proceed, as in you get the poles and get your root locus. So this is, sometimes a question will come to this, so you force it to this form. So from there you can proceed with what we did today. If you guys, you don't have anything, any question, I wish to stop from here. Next week, we'll start frequency response. No? Hello? Andrew, I can't hear. There is no question. So I'll stop my sharing if there is no question. So let's meet next week for frequency response. In case you have any problem as you are doing these questions, you can just write a small note in comment under that question in Google Classroom, so that I can assist. I'll post these notes, type notes, and maybe question made by Monday next week. So let's meet next week. So.
Yes, thank you.
Okay, welcome. This went very well. I don't know, is it because of Zoom?